Hello, everyone. Today we are going to talk about a special type of series, which is called alternating series. What are alternating series? It's a special series where terms are alternating in sign. So they are positive, negative, positive, negative, positive, negative, or negative, positive, negative, positive, negative, positive. So I'm going to write down terms alternate in sign. For example, the series which is going to look like this: 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1 over 5. You see that we do have terms which are looking like harmonic series, right? Like 1 over n. But we do have alternation: positive term, negative term, positive term, negative term, positive term, negative term, and so on. I'm going to write them down as like a formula. And as the formulas are going to look like this: negative 1 to the power of n minus 1 multiplied by 1 over n. So n equals from 1 to 0. So here, 1 over n is like a numerical value of a series, like 1, 1/2, 1 over 3, 1 over 4, 1 over 5. Minus 1 here is telling us that the sign is going to change. When you set up n equals 1, it's going to be 1 minus 1, 0. So minus 1 to the power of 0 is 1. And then you are going to move it to element 2, and that's going to be 2 minus 1, which is going to be 1, right? Minus 1 to the power of 1 is minus. And you increase n, and it's going to alternate plus, minus, plus, minus, plus, minus. Okay, the series over here is called alternating harmonic. So normal harmonic has only positive terms. Alternating harmonic has alternating terms. Okay, so this expression describes a sign. And if you start your series with negative term, like minus, plus, minus, plus, minus, plus, then you just drop this minus this one, minus, minus 1, and it's going to start now with minus 1. Okay, this part is called usually Bn, a numerical part of a series. So usually the terms of alternating series are going to be represented either this way: An equals minus 1 to the power of n minus 1 Bn, where Bn is a positive part of the term, or An equals minus 1 to the power of n Bn. Here, the series starts with negative term. Here, the series starts with positive term. Okay? So, if you write them down like in general, how are they going to look? If you write down this series in general, like minus 1 to the power of n minus 1 Bn, n goes from 1 to infinity. Well, general terms are going to look like this: B1 minus B2 plus B3 minus B4 plus B5 minus, and so on. So we do have kind of set of numbers with alternating signs. B's here are not actually terms, right? Actual terms are a term. B is numerical part of the term or absolute value of the term. I would write down that Bn equals absolute value of an. So if you take a term, strip it out of sign, you are going to get Bn. Well, guys, why alternating series are separated in a separate topic when we learn series? Because their behavior is very interesting. We do know that general harmonic series is divergent, right? Why? Because you take the integral, and it's integral of 1 over x, which is resulting in ln, which goes to infinity. So improper integral, similar to the series, is divergent, so harmonic series is divergent too. Alternating series is going to be a convergent one. And let's kind of look how it can be a convergent series. I'm going to start with like example of how actually convergence is going to work with like general representation of alternating series, and then we are going to talk about alternating harmonic. Okay, So, guys, what I'm going to do, guys, I'm going to consider partial sums. Let me choose a different color. So this is my partial sum number 1, right? And this is my partial sum number 2. And this is my partial sum number 3. Remember that if the series is convergent, then your partial sums must go to a certain number. So our question is, are they going to a certain number or no? Well, I'm going to draw a number line and start graphing terms of this series B. Let's kind of set up 0 over here and kind of observe how the partial sum is going to behave. Well, I don't know what is going to be B1, but let's imagine that B1 is going to be some kind of number, and I'm going to graph it over here. So this is my B1, right? I'm going to draw an arrow over here, B1. Oh, sorry, not supposed to go over here. Maybe I'm going to just draw it a little bit above so it's not going to attach. So this is B1. It's like you made a step B1. And that's in the same place. It's a first partial sum, right? Second partial sum is going to take B1 minus B2. So I'm kind of going to subtract B2 and go somewhere. I don't know, maybe like over here. This distance, the distance is B2, but actually because we are subtracting it, we are going to land over here at my partial sum number 2. My partial sum number 2 is going to be this one, S2. And then when we add B3, we're kind of going to return back over here, right? So if you kind of place a distance B3 from this point, not from 0, you're going to land up somewhere here. And the partial sum is going to be like this. And you see that if your terms are decreasing in size, you are going to keep doing these steps back and forth, back and forth, back and forth. And eventually your steps, if they are becoming smaller, are going to become very small and going to land up at a certain point and eventually stop at that certain point. And this certain point is actually going to be the limit or the limit of these partial sums or some series. Well, what are the conditions to kind of make it true? Well, what we see that my terms B1, B2, B3 are supposed to decrease. So I'm going to write down that condition number 1 is going to be that Bn plus 1, the next term, supposed to be at least not bigger than the previous term, less or equal. Second, guys, they can decrease, but they not necessarily must go to 0. You know that sometimes terms are decreasing, but they go to a certain limit, for example, 2 over 3, and they don't go to 0. And that's not going to be good for us because we are going to keep doing steps forward and backward, forward, backward. Remember the series plus minus 1, like you have 1 minus 1, 1 minus 1, 1 minus 1. This series does not have a limit because it keeps jumping. The sum is going to keep jumping between 0 and 1. Right? So besides that terms are decreasing, we are going to request that the limit of a term as n approaches infinity is supposed to go to 0. So our steps must become smaller. Then this picture is going to work and we are going to be the limit. These two conditions are actually going to form so-called alternating series tests. Alternating series test. Have alternating series if numerical value of a term is decreasing and the limit is equal to 0, then the series is going to be convergent. Is convergent. Let's see how it works on our alternating series, which we had in harmonic. So I'm going to rewrite alternating harmonic. So alternating harmonic. Which is going to look 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 and plus and so on. So what we have, what is Bn here? Bn is 1 over n. Again, Bn is the part of the term without a sign. It's 1 over n, right? So I'm going to check condition number 1. So Bn plus 1 supposed to be less or equal than just bn? Well, I'm just going to write down what is bn plus 1. Bn plus 1 is n plus 1 here, less or equal than 1 over n. Kind of checks because it's obvious, like the smaller fraction is going to become smaller. Sorry for the interruption. My vacuum cleaner started working and suddenly I had to kind of remove it. Otherwise, it's going to be too noisy. So you see that the terms are decreasing. Here, it's obvious. If you divide 1 over 3, it's going to be less than 1 over 2, right? But in some cases, it's not going to be that obvious, and we'll need to do extra investigation. Number 2, condition number 2 is going to be that the limit of the term, limit of bn as n approaches infinity. Well, let's calculate it. Limit of 1 over n as n approaches infinity, kind of 0. So second condition checks. We are going to say that by alternating series test, the series is convergent. Well, guys, now question is, if one of these conditions is broken, is it still going to be convergent? Well, we really don't know. This test works only one direction, means that if both conditions check, it's convergent. But if one of them is broken or both are broken, we cannot tell whether it's kind of going to be divergent necessarily. It still can be convergent, but the test is not going to see this. The test is not sensitive enough to see convergence if one of these two conditions broken. Usually, guys, if the limit of the term does not go to 0, we know what happens. Divergence test starts working because if the limit goes to a different number than 0, means that kind of term does not go to 0, term does not go to 0, the series is divergent by divergence test. But again, maybe this one is not going to work. Maybe the first condition is not going to work. So usually we can not tell next sentence. The series is divergent by alternating series test. No, alternating series test can make only one conclusion. The series is convergent. If it does not work, it does not mean that it's divergent automatically. Yes, it's going to be divergent, but the test which you use to specify this is going to be probably a different one. Let me consider a couple of examples. Well, other than alternating harmonic series, of course. Okay. Usually the test is very easy to use, but in some questions, maybe like you will need extra work. I'm going to consider examples where you can have troubles. For example, alternating series, which is going to start with 1n at infinity, and that's minus 1 to the power of n, 3n over 4n minus 1. Well, nice alternating series. How do we know it's alternating? Because we do have the coefficient of minus 1 to the power of n. Again, it's not going to change the number, but it's going to change the sign of the term. Now, what is bn here? This is bn, the part which we are going to look for alternating series test. Let's check condition number 2 first. Why I'm doing that? Because actually it's much easier to check the limit than to prove inequality. So I'm going to check, I'm planning to use alternating series test and checking condition 2 that a limit of a term goes to 0. 3n over 4n minus 1. Well, if I divide by n, both numerator and denominator, I'm going to get 3, 4 minus 1 over n, right? And when n goes to infinity, this part will go to 0, and the answer is 3 over 4. You see that it's not equal to 0, so I'm going to write specifically that alternating series test does not work. But as I usually said that when alternating series test does not work, we can use other tests. And I will use divergence test. Why? I suspect that because term goes in generally to 3 over 4, maybe divergence test is going to give us something. For divergence test, I'll need to investigate actually a limit of the whole term, not just the numerical part of the term. So I'm going to write down minus 1 to the power of n, 3n, 4n minus 1, a limit as n approaches infinity. Well, guys, what can I tell about this limit? Well, I know that when I don't have minus 1, the limit is 3 over 4. But when I do have minus 1, actually, the terms with n equals, for example, 2, 4, and like all even terms will go to 3 over 4, right? Odd terms, which like n equals 1, n equals 3, will go to negative 3 over 4. So actually, the term over here is going to jump at infinity between 3 over 4 and negative 3 over 4. In this case, we say that limit does not exist. So we're going to say that by divergence test, the series is divergent because series limit must be equal to 0 if the series is convergent. This is going to prove that it's divergent. Limit does not exist means that by divergence test, that series is divergent. Divergent. Sorry. By divergence test. So again, my alternating series test did not work, but I applied a different test and it gave me divergent series. Yeah. Usually that's a good idea to start your check with a limit because limit is much easier to check than inequality. Okay, let's consider a good example now. That was example number 1. We are going to consider example number 2. Example number 2 supposed to be some positive example, right? So I'm going to consider a series as minus 1 to the power of n plus 1. Sometimes people put instead of n minus 1, n plus 1. It does not matter, actually. It's still going to start with like series with positive term. And even sometimes this minus 1 is going to come as a numerator of a fraction. And that's okay to have it as numerator of a fraction. I put it separately because I know that lots of people confuse this minus 1 with actually changing the power. I'm going to put it separately, but normally people can have it together with a fraction. I'm going to start with condition number 2. So my plan is to use alternating series test. Use alternating series test. Okay, condition number 2, limit. And limit again, just of Bn, right? Bn here is this expression. And that's going to be a limit of n squared over n cubed plus 1, and goes to infinity. So if I divide here by n squared, I'm going to get 1 here, and 1 over n squared here, right? N goes to infinity. This goes to 0, right? And I have 1 over n, which will also go to 0 just because n goes to infinity. So the first condition checks. How about the second condition? The condition that the term n plus 1 is less or equal than the term n. Question. Well, if you write them down, the terms, it's not going to be very obvious that the terms are satisfying inequality. I'm going to write down inequality, but we're not going to actually check direct inequality. So we'll need to show that this is true. And you'll probably tell me, well, it's going to be true, 100%. No, guys, look at this fraction. If we changed only denominator and made it bigger, the fraction is going to be smaller. But here we also have a change in numerator, which is making the fraction bigger, actually. So denominator change and numerator change are working against each other. So it's not obvious whether the whole fraction is going to decrease or increase when we do this. Well, we suspect that it's going to decrease because we do see that the limit goes to 0, right? Otherwise, if it's not decreasing, how the limit would go to 0? But to prove inequality is not going to be easy if you do the direct inequality. What I'm going to do, guys, I'm going to use a functional approach. So use functional approach. What is functional approach? Instead of term Bn, I'm going to consider a function which is going to be f of x. Oh, sorry, is it here supposed to be like maybe f of x squared over x cubed plus 1. And I'm going to show that the function is decreasing. If the function is decreasing, then the terms are going to decrease too. Sometimes it's only way to do it. Sometimes you can just consider inequality and it's going to be easy to show that everything works by inequality. So I'm showing this functional approach just to kind of make sure that you use all possible means to kind of prove your point. So how to show that the function is decreasing? We need to show that derivative is less than 0. And let's calculate that derivative. So what is a derivative? Derivative is going to be quotient rule. Remember, we differentiate numerator first, 2x multiplied by denominator, and then minus, differentiate denominator, 3x squared multiplied by numerator. Sorry, supposed to be 2. And divide by denominator squared. I'm going to simplify it a little bit. I have 2x to the power of 4 minus 3x to the power of 4. So minus x to the power of 4. And here is 2x plus 2x divided over x cubed plus 1 to the power of 2. Well, it's not obvious that it's negative, right? Well, denominator, though it's obvious that it's positive, right? So what happens to numerator? I'm going to consider factoring numerator. That's 2 minus x cubed over here. And denominator is still kind of positive. I'm just going to copy it. Now, for numerator, what are zeros of the numerator? Well, if you make numerator equal to 0, you're going to find there are two zeros. X1 equals 0 and x2 equals cubic root of 2, right? If you solve this, the second one, 2 minus x cubed equals 0. If you solve it, you are going to get this. Let's graph these numbers on number line, because we need to know the sign of derivative. So 0, and there's a cubic root of 2, which is going to be a little bit more than 1. Okay. Now, this, let's check the signs of the derivative on this number line. When x is kind of negative, we are going to have negative number here, and negative number here is going to give us positive. Minus multiplied by plus is going to give us minus, right? Then between 0 and square root, this is positive, but because this is like when it equals to 0, it's going to change the sign. 2 minus, for example, 1 is going to be positive 2. So we are going to have positive. I'm just plugging the point. X equals 1 here and here. So when x is greater than cubic root of 2, let's imagine that 100. It's 100 minus 2 minus 100 to the power of 3, like obviously negative number. And we are going to have minus. So where derivative is negative? Derivative is negative here and here, right? We don't care about this one because my n is greater or equal than 1. We care only about this part. And it looks like derivative is going to be negative over here, except maybe 1 point, which is like actually 1 itself. What we can do with 1? For n equals 1, we can just check it manually. We just can check manually that b1 is less or equal than b2. Just plug them in. So remember that's n squared, which is like 1 over 1 plus 1 is less or equal than what? N squared, which is 2 squared 4 over 2 cube is 8 plus 1, like 8 plus 1. Okay, this one is 4 over 9, and this one is 1 over 2. Well, I would not, oh, well, why did I put an inequality wrong direction? Yeah, the decreasing sequence is supposed to have like next term greater than the previous one. Yeah, sorry, my bad. I put the inequality in the wrong direction. If you go back to the test, let me go back to the test because I did a mistake. We'll need the next term less than the previous one. I accidentally wrote inequality wrong direction. Next term here is this one. It's supposed to be less than the previous. So, well, we see that 4 over 9 is less than 1 over 2, because actually to be 1 over 2, it's supposed to be 4.5 over 9, right? So checks. We're going to say that by alternating series test, the series is convergent. Very good. Yes, well, it's not necessary to do this functional test every time. If you see that inequality is going to work, use inequality. Inequality is much easier to use. But if you see that check of the inequality is too complicated, maybe derivative is going to help you. Sometimes derivative is too complicated and inequality is much easier to check. So what else do we need to know about alternating series? Well, another thing which is important about alternating series is like, well, how do we estimate sums of the alternating series? So let me go to our kind of next topic, estimating sums. Of alternating. How to estimate sums of alternating series? Well, imagine that we are dealing with convergent alternating series. So imagine that minus 1 to the power of n bn is a convergent alternating series. So, well, I'm going to write down that the sum of alternating series equals s, and that's going to be, for example, b1 minus b2 plus b3 minus b4 plus b5. Trying to explain how it's going to work. Imagine that we kind of, if it's convergent, we know that any partial sum is going to estimate the sum of series. Remember that we divide actual part sum into partial sum and remainder. Remainder is just like whatever you drop when you kind of consider the series. So that's partial sum number 3 plus remainder of partial sum for 3. And we are going to estimate actual sum with partial sum number 3. Of course, just for example. So is R3 big or too big to draw or too big? We need estimate for remainder. Of course, we can use integral test, but remember, integral test works only for positively termed series. These ones are alternating. So how do we estimate remainder? How big it's going to be? Well, I'm going to repeat my picture with like, going back and forth. Imagine that this is B1, and then you go like B2, then you go B3, and then you go B4, and then you go B5. Then you go many, 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 many times, and eventually you end up with S, right? Now, imagine that you are using sum S3, where it's going to end. It's going to end over here, right? So what is going to be remainder? Well, that's like remainder 3. It's actual sum minus S3. So you just solve this equation. S3 plus remainder 3. Remainder 3, you move S3 over here, and that's going to give you remainder 3. So the difference between S and S3 is coming over here, is going to be this distance. That's going to be a remainder of 3 terms, right? And if you compare this distance to your next term, which is like B4, you see this distance and B4 is bigger than this distance. So actually, remainder 3 is less than next term, B4. And that's going to be the rule. I'm going to put absolute value over here because sometimes remainder is going to be positive, sometimes negative, depending on like where you kind of go. But that's going to be the rule actually for all series, that remainder of n terms by absolute value, which is actual sum of series minus Sn sum of series, which you use for estimation, is going to be less or equal than Bn plus 1, the next term. So if you consider 3 terms, then remainder of 3 terms is going to be less than term number 4, which is convenient, right? You don't need to integrate anything. You just can look at the next term. The next term is going to be bigger than all the remainder. Well, it's because of this like going back and forth rule. Let me consider example of the series. So it's supposed to be. I don't want to write down in green. I want to write down. Let's do blue. Example. And that was example 3, for example. I'm going to consider alternating series test, -1 to the power of n over n factorial. N goes from 0 to infinity. Can we start series from 0? We can start if everything is working, if you're not dividing by 0. We remember that 0 factorial is equal to 1, right? So we're not dividing by 0 over here. And we remember also that 3 factorial, for example, it's 3 by 2 by 1, right? All the numbers multiplied. That n factorial is like all numbers from n to 1 multiplied. So let's check if it's convergent. Use alternating series test to check convergence. Number 2, limit of 1 over n factorial, n goes to infinity. Well, obviously goes to 0 just because when n goes to infinity, all other factors over here go to infinity too, and we are dividing not only by one infinity, we are dividing by a huge number. Now, what is going to be next? Check that bn plus 1 is less or equal than bn. Here I'm going to be careful. What is my bn plus 1? Bn plus 1 is 1 over n plus 1 factorial. It's supposed to be less or equal than 1 over n factorial. Guys, what is n plus 1 factorial? N plus 1 factorial is n plus 1, then the previous term is n, then n minus 1, and then until you reach 1. Basically, n plus 1 factorial is n plus 1 multiplied by n factorial. That's what I'm going to do over here. I'm going to just write it down. This is 1 over n plus 1 n factorial. Here less or equal 1 over n factorial. Now, this one are going to be canceled, and that's a positive number, same on both sides. So I'm going to have an equality 1 over n plus 1 less or equal than 1. Well, if n is greater or equal than like 0, that's true, right? At 0, it's going to be exactly equal, but n equals 1 is going to be like 1 over 2 and so on. You can also simplify it more multiplying by n plus 1. So 1 is less or equal than n plus 1. And if you cancel, n is greater than 0, which is actually like what we have. So we checked. The series is convergent. I'm going to write down convergent by alternating series test. Because we have so many tests already. We have divergence test, integral test, comparison, 2 tests of comparison, right? And alternating series. We'll need to name the test which we use to do comparison, to do convergence. Now, let's see like, wow, if I want accuracy, for example, like if I decide to estimate the sum of this series. So I'm going to write down the next question. What is S with accuracy? Well, I don't know. 0.01, for example. Accuracy 0.01. So what it means in parentheses? That remainder of n terms must be less or equal than 0.01. So I'm dropping something which is less than this. Then I'm going to be happy that I'm not changing my sum too much. So what does it mean, guys? We are going to write down the terms of this series, and they are going to look like 1 over 0 factorial. Let me remind you call the series -1 to the power of n factorial n from 0 to infinity. So when I plug in 0, I'm going to get 1, then minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial and so on. So basically, guys, the idea is that remainder is supposed to be less than this, but I do know that remainder is less or equal than bn plus 1. So if I make bn plus 1 less than 0.01, remainder for sure going to be less. So I'm looking for term which is less than 0.01. Well, 5 factorial. What is 5 factorial? Let me calculate 5 factorial. That's 5 by 4 by 3 by 2 by 1. Maybe it's already enough. So 5 by 4 is going to be 20. 20 by 3 is 60. 60 by 2 is 120. So this is 120. And of course, the whole term is going to be 1 over 120. which is going to be less than 1 over 100, right? Which is 0.01. So maybe that's going to be the first term we draw. How about 4 factorial? Maybe it's enough like to do it up to 4 factorial. I'm going to calculate 4 factorial just in case, because I'm not sure that it's going to be great less than, but most likely yes. 4 by 3 by 2 by 1 is going to be 12, by 2 is going to be 24. So the term is actually 1 over 24, which is not less than 0.1, it's greater than 0.01. So this is going to be my term bn plus 1. And minus is not supposed to come over here, and I accidentally took it inside, right? So this is going to be the first term you draw. And these terms are going to make up your sum. And that's going to be sum of how many terms? 1, 2, 3, 4, 5, right? So you are going to add these 5 terms and have the value for the series estimated. So we're going to write down estimated value of the series is going to be, give me a second, guys. Okay, guys, I took a little pause to write down the terms over here, like, because we need the sum of these 5 terms, 1, 2, 3, 4, 5, right? I wrote the first term is going to be 1, the second term is going to be 1 again, just because it's 1 over 1 factorial. 2 factorial is 2 by 1, it's 1 over 2. 3 factorial is 2 by 1 by 2 by 1 by 2, 1 by 2 by 3, which is 6. And this 4 factorial we already calculated, it's 1 over 24. So these two terms cancel each other, and we have 1 over 2 minus 1 over 6 plus 1 over 24. Let's calculate it, and that's going to be approximately the sum of series with accuracy 0.01. Let's do it very quickly. So I think common denominator is 24 here, right? So we are going to have 12 minus 4 plus 1 over 24. And that's going to give us what? 12 minus 4 is 8, 9 over 24. Well, I think we just need to divide it using a calculator because, let's see what it's going to be. And maybe, guys, I'm doing mistakes somewhere, but all devices in my house keep distracting me. So I'm getting 0.375. So approximately my sum is going to be equal 0.375, and accuracy is going to be 0.01, means that actually we can even round up it and write it down 0.38, because accuracy is already like higher than amount of digits we have. So that's going to be approximately my sum. Our typical problem is going to be estimate the sum with that accuracy. So first, you will need to find which term you will need to drop. Which term you will need to drop, and that's usually going to be called term n plus 1, because you count the rest of the terms before it. And then you find the term and see, okay, we drop this term, and then we count in all the previous ones and kind of calculate the sum. So alternating series are easy to estimate the sum, though you probably will need lots of terms. Factorial case is easy because factorials are growing a lot, and basically term number 5 is already much smaller, like not much smaller, but smaller than 0.01. Okay, okay, guys, so that's it. And I think we are going to continue this section C5, which has like 2 parts, alternating series and absolute convergence. I'm going to talk about absolute convergence in my next lecture because it's going to be too much for one video. Okay, thank you.